Okay, welcome everyone. Welcome to the Energy Institute. I'm Jenny Love, one of the PhD researchers here, looking at, as we make buildings more efficient, what's the effect on internal conditions. So I and the rest of the UCL-Energy Institute are delighted to welcome Richard Partington. I'll just tell you some information about him. Richard is a co-founder and director of Partington Architects, a multidisciplinary practice working in housing, urbanism and regeneration. Richard has expertise in low-energy design through research projects, urban planning and architecture. Richard is architect advisor to the Zero Carbon Hub, including co-chairing the Design versus As-Built Steering Group to investigate the performance gap in new housing. He's also published academic journal papers and taught at several institutions. And you can see the title of this talk is Heat Loss or Heat Gain, Are We Inviting Overheating Problems in New Housing? So before I hand over to Richard, there's a few housekeeping things to say. The fire escapes are located behind the camera and where you came in the main entrance. The structure of the event is Richard will talk for about 45 minutes and then there'll be a Q&A session for 15 minutes. Would you prefer questions as we go along or after?
No, I think it would be good if people do interrupt, especially as we have to have the lights quite bright for filming. And so two of the slides might be a little bit faint. But if it's a technical question that I can't answer, I'll just move on to the next slide very quickly. But,
and there will be some opportunity to ask questions afterwards. At 6:30, we'll all migrate upstairs for drinks and nibbles, where there'll be further opportunities to chat to the speaker if it's okay to stick around for a bit. And then we're aiming to finish the evening by 7:30. And if you don't have a UCL pass, then you'll need to grab someone who's a member of UCL to be able to get out, please. You can do that. Okay, so that's all. So over to you, Richard.
Jenny, thank you. I'm very nervous talking to this audience, being an architect who bunked off most of the services lectures when I was a student. So I had to kind of suggest a caveat really to what I say, which is that I'm not from a scientific background. I'm a practitioner. But I have been very fortunate in the last few years to be in the same room as house builders and people with a research and scientific background, both people from UCL and also from Leeds Med. And so we've been hearing on the various government task groups looking at policy, really what the kind of first-hand effects of kind of recent initiatives, and particularly the drive towards zero carbon. I'm also very fortunate that in my practice we sort of combine research work and policy work and actual building design. And we have one project in particular, Derwentthorpe, which has been running for nearly 7 years now, where the Joseph Rowntree Foundation has been very slowly and methodically working through all of the issues that have been raised by things like zero carbon homes policy and the Code for Sustainable Homes, and have been measuring and testing and monitoring as they've gone along. So we're able in my practice to see projects delivered on site, to engage with people who are making policy, but also we get asked to write guidance, particularly for organisations like Joseph Rowntree and the NHBC Foundation. So trying to simplify quite complicated issues for a less well-informed audience. So in case of NHBC, for the small builder or for the small developer. And that's how we got involved in this overheating discussion. Notes, there's lots of stuff that's available that you can go back to. And the general structure is that I'm going to talk about the things that we think are contributing to potential overheating problems. And then we're going to talk about some of the things that are potential ways of mitigating the risk. So slides with an orange band on top are what we think might be problems. Blue ones are solutions. And the grey ones are case studies, or where I'm just wandering off the point a little bit to talk about some of the buildings that I've designed. So, the kind of first principles that everybody understands, you know, are that there are external factors and internal factors that can create a condition of overheating. So exposure to direct solar radiation, the likelihood that new homes have more gadgets and appliances in them, the kind of metabolic gains, the things that cause the buildup of heat internally. And that's fairly straightforward. But looking at the evidence, and there's particularly research that's been published by BRE, again for an HPC Foundation, looking at all of the incidences of overheating that they've gone to and actually measured. One of the really striking issues is that there very often isn't a single cause, a single phenomena that you can kind of point a finger at and say, that's what's happened here, it needs to be corrected. The only consistent and common theme in the evidence that's available is that most homes that suffer from some kind of overheating are deficient in ventilation in some way. Now that might be the design of the windows, it might be the design of a ventilation system, it might even be a sort of external factor. So, you know, the location of the home, is it close to a busy road, a kind of potential security issue, a source of noise or pollution? Is there some reason why the occupiers don't necessarily ventilate the home as well as they should be? And so the kind of theme that I want to try and explore a little bit is the way that we predict overheating and the way that we evaluate it and the tools that we use, and whether they actually look kind of far enough outside the dwelling itself at some of these external and contextual factors. And this is where there has to be a relationship between designers who should be doing that thinking and scientists and engineers who should be able to do the prediction. But the underlying problem that does seem to be very clear is that everything we do at the moment in terms of low energy design is really geared around the winter performance of the house. So everything we do is to conserve heat. You know, we make homes very airtight, we make them super insulated, we have very high grade you know, external glazing, we worry about thermal bridging. The whole of the low carbon policy is based on the idea that we save heat in winter. There's not much thought gone into the consequences of that in the summertime. So it is true that a well-insulated home will keep the heat out as well, but it's also more thermally sensitive. So a small amount of additional heat in a contemporary well-insulated home will create a much higher rise of temperature. And this is where things are really tricky if you work in housing, because actually the kind of definitions we use and the way that we describe overheating are not very helpful, and there isn't very much consensus. So whereas in non-domestic design, in sort of schools and offices, you can talk about, you know, the number of hours a year when a certain temperature is exceeded, or you can talk about the number of days. That's quite useful for an office manager if you say, well, you might be 10 days a year when the temperatures are sort of not very tolerable. That's when your workforce will be less productive. In housing design, what you're kind of more interested in is when does the temperature get so high that it's actually stressful. So saying that you've got X number of hours a year above 25 degrees C doesn't really tell you very much. What you want to know is when the temperature is really scorching, you know, or you have several consecutive days where the temperature is very high. So the kind of measures that we use are not necessarily very helpful, and they don't account for some of the other contributing factors to sort of heat stress, so for instance humidity, and they're interpreted very differently by the different modeling tools that we use. So if you model a home in SAP, and this was something we did some work on Welsh Passive House for some guidance to government on the future of the SAP model, the compliance model. Lots of people were saying that SAP wasn't really adequate for predicting overheating. In truth, it doesn't do that. It gives you a kind of indication of risk. But these homes modeled in PHPP suggested that there was no overheating at all. Because PHPP, you're allowed to start, or you're encouraged to start to think about some of the external factors. So shading, you have much more information about microclimate and the weather data for your particular site. But actually, the test of overheating in PHPP is a pretty loose one. You've got to exceed 25 degrees for more than 10% of the year. And that's a whole house model, and that's an average figure. So it's not really telling you whether a specific space on the southwest corner is really scorching. It's kind of giving you a very generalized result. The overheating test in SAP, when we modeled these homes, actually did say there's a risk in August and actually raised temperatures a medium risk in July. But again, that's a model that's averaging. And of course, you apply the SAP model quite late in the design process. If it's part of the compliance regime, you know, you've already got your planning consent, you're thinking about preparing for building regs, suddenly SAP tells you that you've got too much glazing area. That's actually a bit late in the process to make that discovery. So there's not much consistency in about the conventions, and there's not much consistency in the way that those conventions are inbuilt into the predictive tools. But we are dealing with a different beast now. You know, historically, a home would have been quite leaky. You would have had lots of mechanisms for air movement, inherently more air changes per hour, and probably a home that you were more, in a way, responding to kind of naturally and instinctively. In an older home, people tend to leave windows open more, tend to throw them open in the summer. If you live in a really super insulated home with MVHR, experience tends to suggest people don't know how that home should react in the summer. So you know to keep the windows open in the winter, but what do you do in summertime? And of course, the one thing that we're all ignoring is that we tend to make predictions based on historic weather data. So SAP takes the last 2 decades of fairly reliable information, but it's historical information. It's not looking ahead to a climate in 2050 or 2080. And if you read the primer that Bill Gethin produced for the Technology Strategy Board, it gives you a really good introduction into the kind of weather that we might, so climate we might expect in 30 and 50 years' time, and also the weather that might result from that and the impacts. That information is very difficult to convey in a talk. You have to really spend some time poring over the graphs. And it's almost impossible to say probabilistic more than once in a talk without tripping up. So I leave that to Bill and other people. But in London, we've sort of got a preview of what's going to be happening. In London, our temperatures are 3 or 4 degrees higher than in the cities in the northwest and northeast, Manchester and Liverpool and Newcastle in summertime. And we're really beginning to see the effects of having, you know, a very hard surfaced environment, comparatively little landscaping, cooling from natural transpiration. We're beginning to see cooling devices employed, you know, for things like the 24-hour supermarket that are effectively chucking heat into the environment day and night. So one of the real difficult phenomena with the urban heat island is that there isn't a change in temperature between day and night. There isn't a time during the kind of 24-hour cycle when you could introduce cool air into a home to cool it down. And when we were doing the guide for NHBC and their small house builders, we thought we were kind of over-egging it a little bit with this illustration, you know, everything that could go wrong in an urban environment going wrong, everything heating up during the day and radiating heat back out at night. And then about 2 months later, I was cycling down City Road and saw this, you know, and actually house builders rarely build things that accurately to the drawings. It's a brilliant representation of what we'd put in the guide. And, you know, the poor people living here, these things are fighting all the time. In fact, this is what happens in a convenience store. You've got chiller cabinets, you know, that need to be cooled 24 hours a day, and you've got external temperatures within those spaces. So within the space, you've got heating and cooling going on simultaneously, and these things are cranking out heat, you know, 12 to the dozen, all day and all night. And there was some very interesting work done by Ayub Pathan, who was at UCL a few years ago working on his PhD, I think, looking at just measuring temperatures in a range of London dwellings over the summer of 2010, which wasn't a particularly hot year. And this is just an extract from that. So, you know, it's dangerous to take, you know, one small sample of data from one dwelling. But I do know that this particular flat has got minimal amount of south-facing glazing. The person who lives in this flat works for me and is a graduate from the master's program here. So I know she's never at home. She's always working very hard. She's underpaid, so the flat's not full of gadgets and big plasma TVs and things like that. But you can see that June to September, temperatures really rarely dropped below 25 degrees. So the green and the blue traces are the bedroom and the living room. External temperatures sometimes were 10 degrees lower. So that's quite alarming in a fairly benign summer on a flat that isn't particularly poorly orientated. So the other things that, you know, are kind of received wisdom in housing design that we're now having to think about again are the simple things to do with orientation. House builders tend to have standard house types, and they just stamp them out on a layout regardless of the orientation. But a very well insulated, you know, 2010 or 2013 building regs compliant home now, if you switch it round so that the glazing is suddenly facing southwest, you're going to have a completely different performance in summertime from the same house with most of the glazing facing north. And you think, well, that's just a matter of adjustment and thinking a little bit harder about how you design and site homes. But even passive house projects, and this is the Welsh passive house again, typical summer's day in Ebervale. Two different versions of passive house by the same architect. So on the left-hand side, what people traditionally associate with passive house design, living spaces on the southern side, large areas of glazing, doing the most you can to maximize passive solar gains. This version, which is intended to be a prototype for affordable housing, actually just took the view that you would minimize fabric losses. You would do your best to keep in, you wouldn't try and do any kind of clever games with maximizing solar gains in winter. And not surprisingly, this home overheats. And it overheats quite frighteningly at certain times. It doesn't do some of the things that passive house advocates would suggest. You know, for instance, having a large roof overhang on the south orientation to at least protect the bedroom windows on the upper floor. And it tries to use technology to counter that effect. And this is interesting, I think, because it's not really how I think we should react to the problem. You know, the nice thing about a house in the country is that when you sit in your living room, you can see the garden and you can see the countryside. And you'll notice that the back door doesn't have the blinds on it. There was a few teething problems with this automated system. And when the occupiers went out in the garden on a grey day and suddenly the sun came out, all the blinds came down, and you locked out the back door because you're stuck in the garden. And of course the things are pretty willful. You know, they wanted to show themselves in winter as well. So when you did want the useful winter gains, again, down came the automated blinds. I think we need to think about ventilation more than just you know, protecting the dwelling from external solar radiant. So another, this is an orange one. This is an orange one, everybody, so this is a risk. We put thermal mass firmly and squarely in the category of could be a risk. And that kind of runs slightly counter to what all architects learned, if they did learn anything at university, which is thermal mass is a great thing, and you know, all buildings must have thermal mass. The issue really is that the thermal mass needs to be used intelligently. It is just a heat store. So if it's storing heat at the wrong time and radiating it back out at the wrong time, it's not going to help you in the slightest. And these oversimplified graphs sort of illustrate that, really. Thermal mass can be beneficial in kind of lopping and delaying that heating and cooling cycle. But if you get progressive days when the temperature gains exceed the losses, you will just crank that internal temperature up. It'll have the same kind of profile of gaining and losing heat, but over time there will be a net gain. So the other thing to be wary of is architects' drawings with ventilation paths on them and blue arrows turning to red arrows, because you can absolutely guarantee that air circulation won't do anything like the architect said it would on his section. But just a diversion for a little bit, you know, we kind of understand thermal mass in office design. And you can start to make provision for instance, on a shallow plan building like this one, it's one of my buildings for a housing association, you can start to think about, well, what happens if we have cellular spaces? Can we still get air movement across that slab and ventilate it at night? You can start to have elaborate control systems with the BMS that open kind of hopper lights at the perimeter and get good air movement on the slab. You can get the slab to cool down overnight. You can think about the kind of ventilation paths. You can do clever things where you start to increase the surface area so that when cool's radiated back during the day, this is the design above the cellular offices, so a kind of perforated grille to allow air movement. And then that was very cleverly combined with a blind and the automatic vent behind that, so it was also an insect mesh and stopped birds coming in and things, and a wonderful piece of lighting design where, you know, the uplight is just catching the cusp of that recess in the concrete slab. But how do you apply those things to a house? You want the office to be cool during the day. Actually, you want the house to be cool at night. So the time in the office when you're doing all the active things to cool it down are probably going to conflict with what you want in a bedroom at night time. In other words, not gallons of air kind of circulating around the space and big ventilation systems. And the complexity to try and get these things to work on the scale of a house seems to me to be a little bit inappropriate for a dwelling. And so here are celebrated, award-winning architects, very, you know, well-known, incredible pedigree of doing low-energy, non-residential buildings, designing a housing scheme in Brighton with lots of thermal mass. Thermal mass is good. That's what all architects have learned in their services kind of lectures. But here there are single aspect units and a distributed heating system, which I'll talk about a little bit in a minute as well. And what I think we'll find when the data is published in a couple of weeks' time, because this is one of the BPE, TSB building performance projects, is that there are some really serious overheating problems. And Rachel Capon at the Good Homes Alliance has been looking at what might be causing that and whether there are differences between some of the predominantly single aspect units, the red ones, and the occasional dual aspect one on the corner here. So there are these recessed sort of garden spaces along the building facade. These spaces are quite well protected and overshadowed, so shaded rather. And there are some windows on the corner of the living space. And she's finding actually there's a really marked difference in the summer conditions in those two. She also thought it would be worth having a look to see whether we can cure this ventilation problem with a mechanical system, because there was a slight misconception on the part of the designers that because the homes had mechanical vent and heat recovery, that system would be doing enough ventilation to purge the heat from inside the dwelling. So Rachel looked at a 2050 medium emissions scenario. So the general kind of base case that everybody refers to, politicians always say, you know, 2050 global warming will have raised kind of temperatures by 2 degrees. So it's the kind of where we think we might be. And even when she increased the ventilation rate by 400%, so up to now 12 or 13 air changes per hour, she still couldn't reduce the temperatures to the target that she'd set as being, you know, comfortable for the bedroom in a dwelling. And there are some fantastic drawings that hopefully will get published showing the scale of that ventilation system in the dwelling. You know, so you've got a big office-sized ventilation unit, and the whole of the soffit of the ceiling is covered in ductwork. Simply an impractical solution, but one that's pretty much the consequence of misunderstanding how to use the properties of the thermal mass. But it's coupled with something else, which we're also seeing in London a huge amount, is that when you start to have services which are fully charged with heat all year round, so if it's just a simple home with a solar collector and a big hot water cylinder, that has a system, a network, a distribution network that is charged with hot water. When you have apartments with common services in corridors, so any of the schemes in London where we're encouraged to connect to district heating systems, you've then got services that are common in the corridor spaces, which are again fully charged with hot water all year round. And the likelihood is you also have a heat exchanger of some kind within the apartment. So whereas an instantaneous boiler is turning on and off when you turn the hot water tap on, the heat exchanger is actually fully charged on the common side of the exchanger with hot water. So you've actually built a radiator into the apartment. And you'll see this is a, you know, again, just to show you how in a way, we're not understanding how these issues relate. This is a demonstration home at the BRE, and this is inside the service cupboard. Immediately the other side of this plasterboard is where your head goes when you sleep in the master bedroom. So this obviously isn't good practice to leave all these surfaces uninsulated, but this is also a really bad piece of planning, kind of, living accommodation and services. So there's just a hotspot created by the amount of hot water fully charged in those pipes, and also the heat exchanger in the MVHR unit, which is the bit on the top left-hand corner with all the baker foil coming out of it. Not the best ductwork installation I've ever seen. And even when you correct that, which actually, as after Fionn Stevenson and her team at Nottingham pointed out what was going wrong, you still end up with lots of areas that you can't insulate very well. And in any event, the insulation isn't preventing the heat from escaping, it's just slowing the rate of heat from those. So this is in a London apartment, so you can see here, this is an insulated system, and this is one of the houses that the BRE looked at, and it looks like a kind of reasonable installation. There are obviously areas where there are pipe clips, valves, disconnection valves and things, meters and monitors where it can't be insulated, and then this is the pipework distributing the hot water and the domestic heating system. And the only reason for overheating in this dwelling was a combination of this heat source in the cupboard with the CIU and the fact that it had a very poor ventilation strategy. So the difficult thing for the designer is actually thinking outside the kind of small model that we use, SAP or PHPP, or even some of the dynamic tools, and starting to understand the context a little bit more. And I think that's one of the flaws, actually, in a lot of the work that's been published and done so far. So the effects are cumulative. They extend outside the dwelling. And you can see here, for instance, the effect of external transport infrastructure. These are flats very close to the Hammersmith flyover. The upper floors were all modelled, and it was fairly clear that there was going to be a real need for cooling load. They were all private, so they had cooling built in. The bottom flat is the affordable one that didn't get the benefit of any cooling. It's got a pathetic background ventilation system which connects to the outside above the windows with an attenuator in it, so very small amounts of fresh air coming in. It's affordable housing, so the affordable housing provider says, oh, well, for safety reasons we must put a restrictor on the window, so the window only opens by about 100 mil inwards. It opens inwards within a deep reveal. So actually the only free area that window is giving you is this thin sort of wedge-shaped slot on one side. And there is a really serious, again on the part of designers, misunderstanding about what the ventilation area is when you're having a conversation with the engineer who's advising you on areas and air changes.
Richard, was it infrared reflective glass used on that?
Sorry, on these?
Yes.
I don't know.
And what direction is that facade facing?
This is northwest, so it's actually getting some late evening sun. And the BRE didn't think that the large areas of glazing were really the problem in this particular flat. It was the fact that there just wasn't sufficient ventilation, and even if you could have opened windows a sufficient amount, nobody would have chosen to because of the location, really. It is one of the ones that's written up in it's NF46. It's the evidence review that was published by NHBC. So there's this misunderstanding about ventilation and natural vent, and then there's also this problem of terminology. So we talk about purge ventilation in Part F when we're talking about getting rid of odours and humidity in wet spaces, but we also talk about purge ventilation for overheating. The two things sort of seem to need to be understood a little bit better. This is the guide that was published by the EST about 4 or 5 years ago, and this is where my whole sort of beef about modelling and assumptions really comes to kind of bear, because this is kind of theoretical scientific piece of work, and it does sort of take the view that thermal mass can be beneficial. I'm not disputing that at all. I'm not saying it can't. But to arrive at that conclusion, certain assumptions were made. I don't know if people have seen the output from this study. I've never really understood these diagrams. I mean, they're very alluring, but the splatter, the blob, the center of the splatter is meant to be the number of hours above the 27 degrees set point that they set. And the kind of radius, or the diameter of the blob, is meant to be the distribution within the home. So the guide says that a small blob, low down, so fewer hours of exceedance, is a better strategy. And what they did was take a standard house design and apply, for a lightweight and a heavyweight house, a series of measures, not incrementally, but just testing each one. So testing orientation, testing improved ventilation rates, testing changing the ventilation, the shading. You know, and the underlying conclusion is that, you know, night ventilation and thermal mass is a really good thing. That might be right, but one of the assumptions was that, you see at the top, an equivalent of 25% of the total window area would be open in order that you could achieve 4 or 5 air changes. Now on the face of that, you think, well, 25% of the window area, that's probably pretty straightforward in a home. But when you think about it, I'm not sure that's right at all. If you take a kind of average suburban home, most of the glazing is on the ground floor, on the garden side. And for security reasons, probably at night, you're not going to leave that glazing open. So I'd have said that at least 60% of the total glazing in the home is not available. If you then go to the 40% that's available on the top floor, most bedroom windows are a fixed light and an opening light. It's very rare to see anything else. So of that 40%, half of that's gone. So that takes you down to maybe 20%. Then you can't open the windows fully. And then probably if you think, well, the kids' bedroom is going to have a restrictor on it, so maybe half of those windows are only openable by a very small amount. So probably it's only realistic to get 10% of the glazing area to work properly for ventilation. But this is a piece of kind of abstract scientific work done without actually thinking about what goes on in a dwelling. And I'm very skeptical about whether that's achievable without the designers thinking right from the outset, what does 25% opening area actually mean? How do you achieve that? You know, and you can see the kind of glazing systems that work well for ventilation, for instance, a sash window. You know, you can only ever get 50% of the glazing area to work as free area with a sash window. Most windows now, and especially with modern thermally broken, you know, very well insulated double glazed units, and certainly triple glazed units, have a real limit on how much they can be open, just because the ironmongery, you know, the technology that's to do with supporting the opening window, doesn't allow that opening. We've talked a little bit about shading. When all of those things come together, you know, so trying to keep the sun off, trying to use devices to get ventilation, trying to make secure ventilation, you end up with something that I've designed, which actually didn't start out as a good strategy for dealing with summer overheating. When we were designing these homes in 2006, we were just fixated on passive solar gains, but also on trying to create privacy for a dwelling that was south-facing on a street. So we wanted to have big window areas, but it seemed a bit odd to be only 2 meters from the footpath. You know, it's not Holland after all. We're not all gazing into our friends and neighbors, you know, playing board games in the kitchen. So we had this idea of a winter garden, and we tested it out on an engineer's house, the Gifford house, from about 10 years ago, which was a really sophisticated solution, worked very well. And what we tried to do in this house was actually get some air movement up to a higher part of the house so that you could leave windows open during the day and not worry about the security. So we used the winter garden as a kind of double height space where you could get some better ventilation. You could ventilate the living space on the ground floor. And that's why it has this sort of mesh floor. And it was just about large enough to be able to do things like have a study on the ground floor and an extension of the bedroom space on the floor above. Horrendously difficult to get this work. How do you decide where the thermal barrier is going to be? You know, if you follow the pure physics and assume that the occupier is really going to understand it, then this is the line of thermal barrier and insulation, and this is all single glaze stuff that does the right thing in winter, and in summer it all opens up. Trying to explain that to Joe Public, or even to Barrett, who built these homes, we gave up. Trying to get Arup to conceive a ventilation system that selectively took warm air from the right places of the home, it's also absolute nightmare. Then trying to get that to work on a housing scheme where we'd been really smart, actually. You know, this is my office, so we're pretty clever about these things. Our houses had, you know, two different variations. So you had one which was on the north side of the street, which had the double glazed sort of solar space on the street side, and then we had the one which was on the south side of the street, which needed it on the garden side. So we'd already created a situation where you couldn't replicate the same solution throughout the scheme. But this is what we were kind of aiming for. And it's fiendishly difficult even to get a window to open at the right place at the top of that, and to get some secure, you know, ventilation at the back. I'll show you some other attempts by very worthy architects to get the same things to happen. And it had evolved from a strategy which was more to do with, you know, beneficial solar gains in winter. So this is something we do a lot in my office. We rely on tree planting for shading in summer. It's brilliant. In my garden, it works fantastically well. In the same study as that flat that was over 25 degrees, I've got nearly 80% glazing in my living room, wonderfully shaded by a big pear tree and a willow tree. Whenever we do this on new schemes, you get sticks instead of trees. And the shading doesn't appear for about another 30 years, even if it does kind of materialize. So word of warning about that. But this started as a kind of strategy for passive solar gains. And of course you can't do it everywhere, because in urban design, you know, unless you have a kind of fully solar layout where everything is north-south on east-west streets, there are no way that you can kind of cater for all of the situations. So these poor guys probably are going to get a bit hot. Okay, so some much worse offenders. That's Yorkshire, and people aren't worried about overheating too much at Derwentthorpe. And we've got a lovely lake and, you know, ducks and things, so when it gets too hot you can go outside. This is not so great. This is Victoria. And my prejudice again, I don't like the way that affordable housing is treated differently from private housing. There seems to be some kind of discrimination going on, but this is the wonderful expensive private housing facing south and west. Fantastic big balconies with masses of overhangs. You know, a really good, unintentional, but a really good solution for you know, protecting those dwellings from overheating. This is the affordable housing, so smaller window areas, admittedly, but it's shunted right up against the railway line up Victoria, so the main line coming out of Victoria. The whole scheme has MVHR. It also has a community heating system. And this is the first project where overheating has become a legal issue. So now it's not just not complying with building regs or you've got grumpy tenants. This has got as far as litigation and the whole issue of public health and the liability of the landlord. And the other thing that people forget is that affordable housing tends to be more intensively occupied. There will be more people per unit area of space, and they'll be in the space for longer, and the chances are they'll have the tellies and things on during the day as well. So all of the problems are compounding. And this is the poor guy who really got fed up with it and took the Housing Association to task. But what I really like about this photograph is that he's looking out through his balcony with this super, super high performance glazing because it's by the railway line. Okay, so somebody in environmental health or planning has said, this is terrible, by the railway line, you know, we don't want any of the residents to hear any of that external noise. So you get accustomed to living in this acoustically protected space, which means you have no inclination to open the windows in summer when it's really important that you do. But over here is 19th century Peabody estate. So it's just about as close to the railway line as this new scheme. Sash windows, single glazing. People have always been used to the railway noise and instinctively open their windows in summer. So there's a completely different response just because of the kind of internal environment that's been created. And there are no reports of overheating in this scheme at all. So again, how does a kind of, you know, simulation model pick up the nuances of that particular context? It needs some really intelligent design and some intelligent kind of thinking in the round. So that's the old Peabody stuff, and that's the block on the other side of the railway line. Okay, one last good example, because there seems to be a sort of trend coming in a way a kind of new typology, which is quite interesting, to do with ventilation. And this is a retrofit project where the whole issue about, you know, being on a busy public thoroughfare, you've got spaces that are close to footpaths, visitors, external people and noise, trying to, you know, create a secure way of ventilating, which looks like a good solution to me. Bit of a problem about not being able to put your knickknacks and things on the windowsill, but on the whole, a well-liked solution. And that is coupled with an automatic vent above the staircase, which you can see is quite a difficult thing to achieve in a two-story retrofitted house. You know, there's actually some really serious issues about going from a cold roof to a warm roof within the same construction. But in order that you can access the vent and, you know, repair it if the actuator goes wrong or if the weather detector, you know, fails or if the power fails, you know, there's this whole extra bit of access in here. It's quite elaborate, but it is successful. The occupants of these homes are really comfortable and really feel that the kind of house is just kind of very, very, you know, it's very tolerant of external conditions, just acting on its own. And then that's become the kind of solution of preference really for architects now, because now we can have chimneys on homes again, and we can do things with the roof line because we can make these nice, you know, stack type vents. So this is Kevin MacLeod's thing in Swindon, where I actually have some doubts about the practicality of this, because you can't get to any of that stuff at the top. And they don't seem to have thought about the heat losses through here. So there's a bit of design work to do once you get used to it. But it's interesting that it actually does contribute really positively to the architecture. That would be a pretty unrelenting roofscape without those projections. So just to end and go back to the BRE work, really, the other thing that is really quite frightening is that it would seem that the problems are not just confined to modern homes. I mean, it's pretty easy to predict that there will be serious problems with modern homes, but even people making interventions like installing secondary glazing and a glazing system that doesn't allow for proper vent in a restoration project. Or this one, which is the one that really struck me as being quite interesting, again from the point of view of a designer, because you wouldn't look at that facade and think, well, we're bound to have problems with overheating. I mean, some of the stuff that we're encouraged to do, you know, fully glazed penthouse apartments, where you think, come on, this is going to be a problem. But, you know, what's the proportion of glazing on that facade? Maybe 30% at the most, 25, 30%. But it's all hard surfaces, and you can see from the thermogram, you know, the temperature of the brickwork by mid-afternoon, 60, 70 degrees. So all of those hard surfaces are absorbing heat during the day. At night, when you want to be able to ventilate, you're opening windows and air is being entrained across all these surfaces that are emitting heat, and that air is warming up. And that's probably contributing to that kind of phenomena we saw on that graph where day and night the temperature is just fairly constantly 25, 26 degrees C. So if you read the notes, there's some useful conclusions for you. And then finally...
Where are the notes?
Well, I think they'll be published. Is that right? The slides will be distributed. So
slides on the internet? Yes, on the energy
I think that's right.
Side.
Yeah. And a plug for Bill Gethin's book. So the follow-up to the TSB work was a more comprehensive study, really looking at climate change, but also looking at things like flood risk, ground conditions, whether we're using the right climate data. And I think that's all I have to say. So apologies for the lack of scientific rigor, but you'll see it's not just a question of degrees, temperature. We're on time.
Yeah, absolutely, perfect.
Yeah.
We've got about just under 10 minutes for some questions. I'm
Great.
sure we'll do lots. So, let's start. Say who you are.
Tony Edwards, architect, doing retrofit and preferably good energy retrofits. In Victorian houses,
yes.
Edwardian houses, quite hard, which we haven't talked about a lot or mentioned. Thinking it over a lot, I'm a bit wary of you being too critical about thermal mass.
No.
Because, I mean, I think an awful lot, going along with your deciduous trees idea, which I've looked at too, even ivy is a good screen over a pergola or something. Getting external screens, maybe only in the summer, maybe shop blinds only in the summer. You don't have gale force winter winds to be troublesome. Maybe even adjustable, maybe a bolt.
Yeah, absolutely.
Could be useful in conjunction with. You clearly can't have one thing alone, but I thought that thermal mass was a primary issue, so long as you combined it with good external southerly or east-westerly shading, whether it's vertical or horizontal, and also, especially older houses, what house I'm doing is there's 6 old fireplaces blocked up with a ventilator near the ceiling with a hit or miss ventilator full open in the winter. Very passive, but very good. And I wondered how much you could get the nighttime cooling effect of ventilation by having some time-assisted mechanical ventilation at night. You can certainly on sash windows. Yes, on sash windows you can lock them with only 100 millimeters for security. But is not the nighttime purging a very critical thing in the summer?
Absolutely.
We found in my own home, Victorian home last summer.
Yeah, so I should be more disciplined about the way that I'm being critical of thermal mass, because all I'm saying really is that I'm not sure that the modelling assumptions we make are absolutely right, or that the models are absolutely right, and that we just need to be careful about the kind of received knowledge about thermal mass, because it's different in housing and it's quite difficult to implement. Because if you think most houses have the bedrooms on the top floor, it'd be very hard to persuade a house builder to put extra weight and mass just at the point where he's trying to save money with a lightweight timber truss. But there is a general point, which I absolutely agree with, and I don't think we just really understand the physics well enough, or at least we can't replicate it in a model, which is that my, fully uninsulated, 9-inch traditional Victorian construction with high ceilings, with mass, seems to be a kind of more stable internal environment in the summer. And certainly all of my colleagues who spend a lot of time at the BRE demonstration houses, again, it's not scientific, but we thought that the heavyweight houses felt more comfortable on summer days than the lightweight constructions. So I think all I'm saying is just, don't make the mistake at One Brighton of assuming that because you know how to design a low energy office, that you know how to cool a low energy home, that the two things are not working in quite the same way.
Two strategies, a winter strategy and a summer strategy.
Well, yes. Yes, and of course, the thing that we're not talking about very much are the kind of examples of living in a Mediterranean climate where it's absolutely instinctive to keep shutters closed when the house isn't occupied, to keep the sun off during the day. On the whole, people know when to close windows. If there's a warm wind blowing from a certain direction, you don't want that warm air blowing through your home. Living outside at different times of the day, building homes closer together so there's more, or building streets closer together, a more compact plan so there's more inherent overshadowing. I'm just a little bit nervous about technology being thrown at the problem, because it seems to me that's leading us into a very difficult area.
I want to ask you whether you've done any work on the different performance of different insulation materials, because certainly some of the major companies using natural insulation say that they perform much better, as heat excluders than do the Kingspan polystyrene bundle. And I don't know whether you actually looked at that, because that would be a very crucial element in thinking about what to do about insulating homes if different materials perform differently, not at keeping heat in, but at keeping heat out, and therefore the issue that you've addressed.
Well, certainly when you talk to the people who make sort of materials like hemcrete, they'll make that case very clearly, and they also talk about actually it is beneficial, it would seem, to the winter performance as well, because the kind of lag in heat transfer is beneficial at both times of year. The problem we have, which is to do with the problem with modelling, and it's beginning to surface generally in the discussion about, for instance, in the design versus as-built forum, is kind of steady state model is good up to a certain point, but actually it doesn't replicate what really happens in a home. So when you get to the very kind of optimized level of modelling, just assuming that heat's always going in the same direction at a certain rate isn't a very suitable assumption, really. Again, I'm personally very nervous about the kind of synthetic materials, and again, I'm afraid I think it's my prejudice, so I'm not really qualified to say that they're wrong or right. But it does. I don't know if you've seen the slide that Tom Woolley has of his son in bed under a duck-down duvet and then under a plastic sheet, and he's saying that both are keeping him equally warm, but would you have your young boy under this kind of sweaty plastic, that's a little bit of a kind of stretched analogy. I don't know, to give you an illustration on the questions about which insulations work well in a cavity wall construction, for instance, we can't even decide whether rigid insulation and a full fill insulation work effectively, and whether the conventions for predicting those U values work. So we're a long way off being able to understand whether some of these materials that react differently in a dynamic situation are helpful.
Thank you. I mean, all I would say is that for many reasons, I think there are huge problems about polystyrene break. But it does seem to me that your whole issue about overheating, which I quite take as a very important issue, if natural insulation materials are actually, there is a case to be made that they perform better in relation to overheating, this would seem to be a very good reason for something like UCL to actually put some money into actually starting to model and examine how they function.
And starting to measure. I mean, I think that's just we're very short of data on how modern homes perform. And there is a general, again, there's a general debate about do we have to go to this point where we need mechanical vent and heat recovery? The heating season is reducing over time. The amount of heat we have to recover in a warming climate is reducing. Is that actually the right way to be heading? And we know from some of the DCLG funded work, looking at parallel schemes in Austria, that actually where they've got really, really good understanding of building technology, that the focus and the concern is all about overheating. It's not about whether the homes are performing well enough in winter. They kind of crack that, but worry actually whether it's led them to a really difficult position in the summertime.
Should we have one last one, I think, Simon?
Simon Roberts from Arup. Do you know the Passive Design Assistant?
No, I don't.
Free software has been out for a couple of years. From Arup Concrete Centre, sourced by TSB. It's where you can take a single room, choose materials, choose the shading dimensions, air change, temperatures. And I think the point is to get in early in design, where you test out small windows and orientations. I mean, we tend to immediately kind of gravitate towards sort of dynamic tools, which actually is very difficult in housing design to justify that kind of level of interrogation and expense and kind of modelling. And what makes me slightly sceptical about those tools is that from the designer's perspective, unless you have a very good relationship with the person doing the modelling, you're very remote from the assumptions that are being made. So even in office design, we've seen outputs from models that are just completely counterintuitive, because it just happens that on the day that the weather data was uploaded, it wasn't typical. And so you see models where the southwest zone of an office isn't the hottest at 4 o'clock in the afternoon. You say, well, that can't be right. But it seems that we do need to have more interactive tools that designers can understand. We also need a more literate group of designers, because obviously, these things just aren't well enough understood by the design professions generally.
Well, it's time to go to drink, but before we do, please join me in thanking Richard for a fascinating talk.